Hi everyone, I'm going to talk about how to interactively learn reward functions for reinforcement learning, and this is joint work with the people listed on the slide. So as you probably know, reinforcement learning has been very successful in solving complex tasks. However, if you think about what kind of tasks it has been successful on, you will probably think about playing video games or similar well-defined tasks. One property that these environments have in common is that they provide a well-specified reward function, such as the in-game score in Atari games. On the other hand, if you think about applications we might want to use RL for in the real world, such as autonomous driving or virtual assistants, it's much less clear how to define a reward function. Because of this, there has been more interest recently in interactively learning reward functions from human feedback. However, interactions with humans can be very expensive, which is why we should want to do active learning in these situations. There has been some prior work on active reward learning. However, previous approaches are, for one, mostly designed for very specific query types, such as comparisons of full trajectories or numerical evaluations of trajectories. And secondly, these approaches often use approaches that uniformly reduce the uncertainty over the state space, which is not really aligned with the goal of RL, which is ultimately to find a good policy. So let me illustrate this point in a simple example. Consider this robot, which wants to collect food from the grid world for a human user. The robot can only walk 4 time steps, so it has to decide which food to collect. However, it doesn't know the user's preferences directly, but the user knows their preferences, of course. So now the robot can ask the user about a specific item, and the user will respond with the value of this item. So how many questions does the robot have to ask to figure out the best policy here? Well, if the observations are noise-free, it can solve the task using 4 questions by simply asking the user about all items in the environment. However, it turns out the robot can do much better if it considers the environment dynamics in more detail. So if we assume that collecting more food is always better, then there are only 2 policies that are potentially optimal, either collecting the cherry and the apple or collecting the cherry and the corn. Importantly, the cherry will always be collected because it's on the way to collecting something else, and the pear will never be collected because it's not reachable for the robot. This means the robot can find the optimal policy with only 2 queries to the user, namely asking about the apple and asking about the corn. Let's move to a more general setup. In normal RL, the agent interacts with the environment by taking actions in a given state, and the environment then returns the next state as well as a reward signal. Instead, we assume that the environment does not provide a reward signal directly, but there is a user which knows something about the reward, and the agent can make queries to the user, which responds with information about the reward. These queries can, for example, ask for the return of a trajectory which the user provides, or it could ask, the query could ask the user to compare 2 states, and the user gives their preference. However, the general method that I'm going to propose works for arbitrary query types, which is why I will just write Q and Y here. Now, throughout this interaction with the user, the agent can learn a model of the reward function, which I denote with our hat, and it can then use the model as a replacement for the environment's reward function and run any RL algorithm just using the model. And in this setting, the key question we have to ask is how should the agent select which queries to make to the user? So this is the key question about active learning here that we're going to answer. To introduce the approach that I want to introduce, let's revisit this grid world example. So here, what we observed is that if the agent considers potentially optimal policies in the environment, then it can infer which states it has to query about. And I will now describe how we can encode this in a general acquisition function to do active learning with. The first step is to consider 2 plausibly optimal policies, as we did in the example. Now you can think of the goal of RL as to distinguish these policies, to find out which one is optimal. So we can ask the question, how do policies pi1 and pi2 differ? And we can answer it by considering the difference in expected returns of these 2 policies. This is the quantity we somehow want to learn about. In our example, the return of pi1 is given by the reward of the cherry and the reward of the apple, and the return of pi2 is given by the reward of the cherry and the reward of the corn. And also we can see that the difference between the 2 policies only depends on the reward of the apple and the reward of the corn. The final step of our method is to select observations that help the most to distinguish the 2 policies pi1 and pi2, which we formalize using this information gain objective here. So by maximizing this information gain, we select queries that are most informative for distinguishing plausibly optimal policies, which is ultimately the objective of RL. There's one component that I skipped over here, which I now want to talk about, which is how do we find these potentially optimal policies in the first place. And so we essentially combine two ideas to do that. The first one is Thompson sampling. So we sample a set of reward functions from the agent's current belief over rewards, and then we find policies that optimize these samples. And this gives us a set of candidate policies that represent the agent's current belief about which policies are optimal. And then to select two policies from the set, we maximize the entropy of the difference in return between policies. So this exactly gives us two policies that the current model is most uncertain about. So to put all pieces together, I'm going to now present to you the algorithm we call information-directed reward learning. And we start by initializing a Bayesian reward model and obtaining an initial set of candidate policies using the Thompson sampling procedure I just described. And then in each iteration, we first select two policies with the highest entropy in the difference of their returns. So the policies the model is most uncertain about. And then we select queries that maximally reduce our uncertainty about these two policies. Finally, we make a query to the user and update our model. And we can then repeat this loop as often as we want, or as many queries as we can make. For computational reasons, we might not want to update the candidate policies in every step, but just like reasonably often. Ultimately, when some convergence criterion is reached, or we have exhausted a budget of queries, then we exit this loop and select a policy that that optimizes the mean estimate of the reward model. We have considered two concrete implementations of this algorithm, one using Gaussian process reward models and one using deep neural networks, as well as some approximations. However, in this presentation, I will show you results from the implementation with GPs, which are particularly nice because this implementation can do all the computations analytically, and so we can compute or implement this algorithm exactly. However, I will skip some of the details of the implementation, so you can ask me later or check out the paper if you're interested in more details. So let me now move on to show you some results that we have obtained using this algorithm. So we first looked at some toy environments. So one environment is a chain of states in which the agent moves to the right in the first part of the chain, and it can freely move left and right in the second part. Another environment we call junction starts with a chain of states and then leads to a junction in which the agent has to decide between two paths to follow. In each path, it will randomly move left and right. So the only decision the agent can really make is at this junction whether to go up or to go down. Finally, we have some grid world environments that are very similar to the example I showed before. We assume that the agent has a fixed budget of queries, either about the reward of individual states or queries that compare to states. Now we compare information-directed reward learning to a prior method called expected policy divergence. We compare to information gained directly on the reward, so this does not consider the environment dynamics. We consider it to expected improvement, which is a heuristic from Bayesian optimization, and we have uniform sampling on the state space kind of as a baseline. Here we will report the regret of the policies that the different methods learn with a fixed budget of queries. So the regret means how much worse the policies are than a policy that is trained on the full true reward function, which the agent does not know here. So this means here lower numbers are better. We see that IDRL outperforms the alternative approaches in almost all of these settings. And to understand why, for example, in this chain, methods that uniformly reduce uncertainty over the state space will also query in the first part of the chain, which does not really help to distinguish policies or to select the optimal policies. And our method, or methods in general that consider the environment dynamics, will also mainly query in the second part of the chain, where the policy can actually change. So this is why they need less queries. In this junction, the EPD method, for example, fails because it does not realize that there's only a single state where the policy can change. Okay, so the next environment we consider is the simple driving simulator, which was proposed in prior work. So here we learn from comparisons of full trajectories. We again evaluate the return of the learned policy, which is the left plot, which is after a fixed number of queries each point. And then we have the cosine similarity of the learned reward model, which tells us how well the learned function matches the true underlying reward function. We compare again information-directed reward learning to EPD and information gain on the reward. Then there is this maximum regret method, which is specifically designed for comparisons of trajectories and uniform sampling. So here is the regret plot, and as you can see, IDRL can learn a good policy faster than any of the other methods. And if you look at the cosine similarity, you can see that in the simple environment, it also learns a similarly good reward function. So there doesn't really seem to be a trade-off between learning a good policy and learning a good reward function here. Finally, let me show you this more complex environment that we designed in the Mojoko simulator. Here, the swimmer robot has to move to the green square in this corridor, and the underlying true reward function it rewards the agent for moving forward before the goal and rewards it for moving backward if it passes the goal. However, this is a linear reward function in some set of features, but the agent does not observe this reward function. We use an off-the-shelf RL algorithm to solve the environment. And we use an exploration policy to provide trajectories from which we can make queries. And from these trajectories, the agent can then query clips, and it observes the sum of reward over these clips. So here are the same plots as before. Again, regret and cosine similarity of the reward. We compare similar algorithms on this environment. And IDRL is able to learn much better policies with a small number of samples. So if you look at these regret plots, you can see the policies get much better early on. However, if you look at the cosine similarity, there seems to be some trade-off with learning a uniformly good approximation. So the reward function learned by IDRL is worse measured by cosine similarity. However, it leads to much better policies, which is ultimately what we care about. To summarize the key takeaways, IDRL provides an acquisition function for active learning for reward functions in RL, which is focused on determining the optimal policy. It improves sample efficiency significantly, measured in terms of policy return in a variety of environments. And yeah, I showed mainly results from an implementation using GP reward models, which we can compute analytically. However, the approach is very general, and it can be used with arbitrary Bayesian reward models and, importantly, arbitrary query types. If you want to learn more, you can find a preprint of the work on arXiv, or you can talk to me later. Thanks a lot.